Hello, welcome. First of all, I would like to thank the organizers of the Trends in Magnetism meeting for allowing me to give you this presentation. And as I wish I would be there with you all in person, but hopefully we'll can be able to do this soon again. So today, I will tell you about our recent work on hybrid Magnon modes. Here's a brief outline of what I want to tell you. First, I'll discuss briefly why hybrid magnons may be of interest for coherent information processing. Then I will discuss in particular on-chip Magnon-PHOTON coupling that we get by integrating magnetic structures with superconducting resonators. Next, I will talk about Magnon-Magnon coupling in multi-layered magnetic systems. And as any good talk, I will have a few brief conclusions in the end for you to take away. So let me get started first, as I said, with hybrid magnons for coherent information processing. So for this crowd, I'm kind of preaching to the choir. But I think most of you are convinced that magnons may play a role in coherent information processing. And here I want to spell out some of the specific advantages as we see it for this purpose. One of the things that makes magnons interesting is that due to their high density of spins, you can generate very strong coupling to other phenomena, for example, like microwave photons. So you can get coupling strengths that are easily in the sub-gigahertz range. Next, magnons can couple to a wide variety of different excitations. We all know they can couple to microwave photons, but they can also couple to optical photons or to lattice vibration phonons. And of course, they can couple to other magnons or even individual spin excitations. So therefore, magnons are very well suited for coupling between different type of excitations. So you can use magnons, for example, to convey microwave photons into optical photons and so on. Another property that is well discussed at this meeting is that magnons have, of course, wave-like properties. They propagate like waves, and so that allows to encode information in amplitude and phase and make use of interference phenomena if you want to build up some logic functionality. From our point of view, what is really very interesting, if you look at modern microwave quantum circuits, these are all based on planar microwave circuitry, and magnetic systems are really very well designed to be integrated with this, as well show in this presentation. But lastly, I think that is probably one of the most exciting opportunities concerning magnons is since magnetization dynamics has its built-in inherent chirality, it also means that it's very easy to get non-reciprocal phenomena. And any of us who works with microwave components knows that, because we use like circulators or bandpass filters or other things that are based on magnetic systems. So one really attractive feature is that we may integrate this non-reciprocity more directly at the device level for microwave devices, for example, in quantum information system, which allows us to isolate noise from the intactor part, from the actual qubits that we may interact with. So To summarize it once more, magnons are really very versatile. You can have a lot of different interactions with photons, phonons, other magnetic excitations. You can integrate them in various different geometries, whether it's planar or three-dimensional cavities. And there's a lot of interesting new physics, actually, like non-reciprocities or spin bumping or dissipative coupling. And we'll discuss some of this in this presentation. Now, ultimately, the ultimate goal may be to utilize magnons also in coherent quantum information technologies. And the first step has already been demonstrated, where a Yig sphere has been coupled to a superconducting qubit through a three-dimensional photon cavity. And it was shown that you can get strong coupling between these magnetic mode and the qubit mode, and that indeed you can read out magnons at the single quantum level. So it's, while most of what I will talk about is still in the classical regime, it is certainly conceivable that you may push this towards using this into the quantum regime as well. Now, here's then our goal. We want to integrate magnonic devices directly into typical microwave quantum circuitry that is commonly used for superconducting quantum systems. Okay, so here I show our example where we integrate a magnetic resonator into a photon resonator based on superconducting structures. So most of the previous investigation of hybrid Magnon-PHOTON systems was based on bulk ferromagnetic materials, where you had like a bulk sphere of Yig that was then placed in a big three-dimensional cavity for microwave photons. And these were used for demonstrating strong Magnon-PHOTON coupling. Now, in contrast, what we wanted to do is using a planar superconducting resonator and integrate a magnetic structure in here. And here you see an optical picture that shows our permalloy stripe integrated on top of the signal line of our superconducting resonator, which is capacitively coupled at the end to further coplanar waveguides. Now, for the photon system, we built the photon system based on niobium nitride. And we chose niobium nitride because it has a fairly high TC, 14 Kelvin, which means that it also can tolerate higher microwave photons than what you typically have in a superconducting system. So it allows to go to higher frequencies. At the same time, for the magnetic system, instead of yttrium iron garnet, which has been commonly used so far, we used a permalloy structure. And the reason for this is that since it's a simple metallic system, it's easy to process and integrate into our devices. But compared to yttrium iron garnet, it actually also has an advantage of having a relatively high saturation magnetization, which makes it easier to have stronger coupling. It has, of course, a disadvantage that the magnetization damping of permalloy is not as good as yttrium iron garnet. So let's go back in detail once more. Here is a larger overview of the whole system that we investigated and how we contacted it for our microwave transmission experiments. Then if we blow in here in the center, here we see the permalloy structure grown on top of the signal line of the superconducting resonator. And if you would look from the side, you would see that we have a small insulating layer between the niobium nitride and the permalloy. So we have some electrical insulation between the two. And the permalloy structure is slightly narrower than the signal line of the superconducting resonator to ensure a homogeneous field distribution. Now, first, what we do is we characterize our superconducting resonator without the permalloy structure. And so what you see here is a transmission measured as a function of frequency at 1.4 Kelvin with relatively low power of minus 55 dBm, so which is equivalent to 4 nanowatts. What you see, we have a quality factor of almost 10,000, so roughly 7,500. So we have a line width of half a gigahertz at this sorry, half a megahertz at a resonant frequency of 5 gigahertz. Now, we also did measure the resonator as a function of magnetic field. And what you see here is the resonator frequency as a function of applied field, with the field either sweeping up or the field sweeping downwards. And what we see is that the resonator frequency does change as a function of magnetic field, and this change is hysteretic. And the reason for this is that as we apply a magnetic field, we introduce additional superconducting vortices in the superconductor, and these superconducting vortices give rise to kinetic inductance, which then changes the resonator frequency. And so we keep this in mind once we compare now our resonator system as it's unloaded in this case to the loaded case once we have the magnetic system added to our structure. So now we look at the system together with the permalloy stripe, and the first thing that we want to do is just characterize the dynamic properties of the permalloy by itself. So for this, what we do is we measure at 1.4 Kelvin, but at relatively high input power, 0 dBm, which renders the superconductor actually normal. And so we can measure the resonance of the permalloy as a function of magnetic field. And we see that the behavior is typical Kittel-like, nothing surprising there. But then what we can do is we can look at the line width of the excitation as a function of the excitation frequency, and we get a reasonably good linear behavior here. And by fitting this, we do get Lifshitz Gilbert damping of around 0.01, a little higher than that. So this is not so unusual for permalloy. It's maybe a little bit higher than what you're used to at room temperature, but typically the damping actually increases towards lower temperatures. So this is pretty much as expected. Now, we can now go back to the complete Magnon-PHOTON hybrid system. So just as a reminder, this is the resonance frequency as a function of magnetic field for just the niobium nitride resonator on its own. And if we compare this now with the niobium nitride resonator, where we have the permalloy device integrated, we see that we now have a distinct mode splitting that occurs right in the region where the Magnon branch crosses over our photon dispersion that we have in our oscillator. So we see this distinct splitting between the modes here. Now we can determine the quality of our superconducting resonator with the permalloy device by just measuring the photon damping rate far away from the Magnon resonance. And when we do this, we now get a line width of about 2 megahertz. So it's slightly worse than for the resonator on its own, but still gives us a quality factor of around 2,500. So we can then use this complete data here to characterize further the coupling of the Magnon system, where the magnetization couples to the RF field of our superconducting resonator. And so we apply the field parallel to the signal line of the resonator where the permalloy sits, so that the RF fields are perpendicular to the magnetization, ensuring the highest possible coupling. So here we plot the same data that we have here, slightly different by just looking at the resonance frequency. And then also here we have the line width of the coupled system. We can analyze this in greater detail by expressing the transmitted power in terms of the coupling coefficient and the individual relaxations of the Magnon system and the photon system, and the Magnon and photon relaxation frequencies. And when we fit this data, which is shown here on this side with the solid lines, we get a coupling constant of about 150 megahertz, which allows us to calculate a cooperativity that's close to 70. So we are well within the strong coupling regime, and we indeed have coherent coupling between the magnons and photons in this system. Now, we would like to analyze this a little bit further and compare this to previous results where there were bulk yttrium iron garnet samples integrated in 3D cavities, while in our case we have permalloy stripes with much smaller volume integrated into our coplanar superconducting resonator. So we can calculate an effective coupling per spin in the permalloy by taking the overall coupling constant and normalize it by the square root of the density of spins. And if we do this, then in our work, we get an effective coupling per spin of 26 hertz, roughly 27 hertz. If we do the same thing for this previous work on bulk yttrium iron garnet spheres, we see that the coupling per spin is significantly lower, essentially 3 to 4 orders of magnitude lower than in our current work. And one of the reasons is that in our case, the filling factor of the magnetic structure within the complete volume of our resonator is much larger. And so that allows for getting much stronger coupling. In fact, one can optimize this even further. And this was nicely shown within the group of Lu Xiaoliu at MIT, who used a similar approach of using a superconducting resonator with permalloy, except they used this lumped element structure, which allowed them to have a coupling per spin that's even an order of magnitude higher than what we had in our structure. So this shows that by further optimizing the resonator design, there's actually still quite a bit of room of improvement for these type of devices. Now, As I said, we had originally the magnetic field along the permalloy stripe, which allowed for the strongest possible coupling. Now we can rotate the direction of the magnetic field until it's perpendicular. And once it's perpendicular, the RF field and the magnetization are parallel and don't couple to each other anymore. And indeed, what we see is if we rotate the magnetic field further and further, the hybridization gap gets reduced until it completely vanishes here. And this reduction of the coupling constant can be explained by a simple geometric factor, as you would expect from the geometry of the system. So that means that we can also easily tailor the coupling strength in the system simply by reorienting the direction of the magnetic field. Note that there's a little gap here in this data around zero field, because of course, even if we apply the field perpendicular at zero field, the magnetization will still be parallel to the permalloy stripe, and there will be some coupling to the RF field at that point. Now, similarly, we can look at what is the role of the volume of the system. We can either make the system thicker, or we make the lateral dimension smaller, and in both cases we can change the volume by a factor of about 3. And what we see is that when we do this for the larger volume, we get the larger coupling. For the smaller coupling, for the smaller volume, we get the smaller coupling. And it's more or less linear with the square root of the volume, as we would expect. So again, this confirms, our picture about the strong coupling in the system. So in the last 10 minutes or so, I want to change topics a little bit and talk about Magnon-Magnon coupling in magnetic bilayer thin films. Now, as I said, one of the goals is to integrate magnetic systems into these microwave quantum circuits, but these quantum circuits are always planar, and so it would be nice to go into the third dimension. And so can we really build up something where then information can also propagate in the third dimension? And here, magnetic systems really have some advantages because it does allow for easy coupling even in the third dimension, where we have different magnetic systems that we can simply stack on top of each other. And we can repeat this further and further to then propagate dynamic information also in the perpendicular direction to your normal planar system. So these kind of ideas have already been investigated by looking at bilayer systems of ferromagnetic layers with yttrium, iron, garnet, where you can have lots of interactions. Here, for example, you see cobalt on top of yttrium, iron, garnet, where you get lots of crossing points with various different standing waves of the yttrium garnet with the cobalt system. Now, one issue which is already illustrated by this data that you encounter is that if you just look at the homogeneous excitations in the yttrium, iron, garnet and your transition metal ferromagnet, the resonance frequency of the transition metal ferromagnet will always be much larger than in the yttrium, iron, garnet because the saturation magnetization is significantly larger. So typically, we cannot get into a regime where the resonance frequencies are the same. So what we want to do is we do want to shift the resonances in the yttrium, iron, garnet to higher frequencies or to lower fields. And one way how this can happen is by using mode that has a finite wavelength. And so when you do that, then you essentially have an additional exchange contribution to the resonance frequency of your spin wave mode. And this additional exchange field contribution goes quadratic with the wave vector. Now, so at the same time, we can have very specific wavelengths defined by the thickness of the yttrium iron garnet layer, so that we have only specific standing spin wave modes allowed, determined by the thickness of that layer. And so if we make this thinner and thinner, this simply means that the wavelength becomes shorter, and we get to larger wave vector transfers. So we can move the resonance further down. So this then is what motivated our experiments, where we use yttrium iron garnet films that are fairly thin, of 100 nanometers, which is like an order of magnitude thinner than what was earlier used with the cobalt layers. And in order to have a similar magnetization, we use then permalloy layers that have a significantly lower thickness with varying thicknesses. So we grow the yttrium iron garnet on gadolinium gallium garnet. We post anneal the structure to get high crystalline yttrium iron garnet. And then before depositing permalloy, we clean the surface a little bit with iron milling, and then add a permalloy structure via sputtering on top of the yttrium iron garnet. And so the goal is then to have a situation like this, where the spin wave mode crosses over with the Kittel mode of the permalloy, so that we get some hybridization gapping here. And indeed, this is what we see here. This is now the resonance field as a function of frequency for our 100 nanometer thick yttrium garnet, 9 nanometer thick permalloy bilayer. Here you see the homogeneous ferromagnetic resonance mode. Here's the first order spin wave mode, and this is the second order spin wave mode, which crosses over with the homogeneous ferromagnetic resonance mode of the permalloy structure here. So we get a crossover roughly at about 10 gigahertz. So in order to better see this crossover, what we'll do is we replot all these resonance modes, but reference them versus the homogeneous ferromagnetic resonance mode in the yttrium iron garnet. So this is what you see here. So of course, the yttrium iron garnet ferromagnetic resonance is then by definition always at 0, even for different frequencies here. And the spin wave modes of the yttrium iron garnet are always at a fixed relative field with respect to the FMR here. And so we see the permalloy mode dispersing nicely through the yttrium iron garnet. And in the crossover regime, we see two well separated individual resonances. Now, again, we can analyze this. We can calculate the coupling from the splitting of these modes, and we can compare it to the individual line widths that we get far away from the coupled regime. And so if we analyze it carefully, we get about 350 megahertz coupling in the frequency domain, which corresponds to 8.4 millitesla in the field domain. And using the measured line widths far away from the crossover, we get a cooperativity of about 6, showing again that we're in the strong coupling regime. But something interesting is there if you look careful at the line width of our resonances as a function of magnetic field. So you see the damping both for the permalloy and the yttrium iron garnet structure, and in between, in the crossover regime, you see that the damping is in between these two structures. But what's interesting is you can see that when we're in the coupling regime, we can have for one mode a damping that's higher than what we expect from the permalloy alone, and for the other mode, we get a damping that's actually lower than what we would expect from the yttrium iron garnet on its own. Now, the way how we can understand this anomaly in the damping is by including also a dissipative coupling between these two modes. So we can introduce a complex coupling where we have the conservative coupling and a dissipative coupling here, and using this conservative coupling is due to a field-like exchange coupling, while the dissipative coupling is due to a damping-like spin pumping coupling. At the same time, we can then see that depending on the relative phase of the modes, if they're in phase, we get an overall suppression of the damping. If they're out of phase, we get an enhanced damping due to this dispersive coupling. Now, we can carefully analyze this more quantitatively, and we see that the dispersive coupling is 2 millitesla, so it's about a third, a fourth or so of the field-like coupling that we have here. So it's non-negligible for the understanding of the dynamics in this system. Now, this brings me to the end. I'm already talking a little bit longer than I should, but I want to introduce the group that really did most of this work, which was the magnetic films group at Argonne, where I was before I moved to Illinois. And this work was really mostly done, spearheaded by E. Lee, who is here, who is now becoming a staff member at the Argonne National Laboratory. So here are all the people that contributed. A lot of folks at the Argonne National work, especially Ely, but also Thomas Polakovic, who was very important in growing the niobium nitride structures, and Valentin Novosad, who brings a lot of the microwave expertise with superconducting structures to the project. We also collaborated with Wei Zhang at Oakland University. We did some of the FMR measurements on the yttrium iron garnet permalloy structures in Bill Bailey's group in Columbia, and we had some theoretical help from Mark Stiles and Vivek Amin at NIST. So here are briefly the conclusions. Magnons can be very versatile information carriers. They can couple to many degrees of freedom. And you can easily get strong coupling in compact on-chip geometries, which may be very interesting for future on-chip device structures. So with that, thank you very much for your attention, and I hope that I'll get an opportunity to answer some of your questions.